All right, so today we're going to talk about how we can use some of those special triangles that we discussed on Friday to create exact values of our trig ratios, so sine, cosine, and tan, and also the reciprocal ratios, secant, cosecant, and cotangent. We're going to do this the exact same way as we did last year. The only difference is now that we're using radians, our angle measurement will be given to us in radians. And the nice thing about using radians with this is I can actually see the reference angle that I need to use in the actual angle itself. So I'll show you what I mean. Okay, so we're just going to kind of follow along with these steps here in order to do our first few. We will start by putting the angle in the correct quadrant, so 5 pi over 6 in the correct quadrant. So just focusing in on this for right now. So when I see pi over 6, I'm going to separate my upper quadrant into 6 equal slices, 3 in the first quadrant and 3 in the second quadrant. I'm going to actually erase some of this after, so if you're using pen, you might not want to draw it like this. But so 6 equal slices, 1, 2, 3, 4, 5, 6. This is 1 pi over 6. 2 pi over 6, 3 pi over 6, 4 pi over 6, and we're looking for 5 pi over 6. It falls right here. Okay, this is why that circle that I showed you, that radian circle, can be useful. If you're ever uncertain, you can take 5 pi over 6 and switch it back into degrees if that helps you place it in the proper quadrant. But I'd like you to start kind of thinking in radians. Okay, so I don't need the rest of these. I'm just going to erase the rest of these here. Just wanted to kind of show you the process of how we place that angle. Okay, so I've got 5 pi over 6. If you remember back to last year when we did questions like this, we needed a reference angle for any angle that was greater than 90 degrees. So any angle that goes into quadrants 2, 3, or 4, we needed a reference angle, which would be the angle between our terminal arm, which is this terminal arm here, and the closest x-axis. So in this case, it's pi. The reference angle is super easy to find here. It's actually just the angle that you see within there, pi over 6. Okay? So that's the angle that's inside that inner corner there. I'll zoom in on here for you. Okay, so this is pi over 6. Our special triangle, this is like a 30, 60, 90 triangle from last year. So pi over 6 is 30 degrees. Our other one is 90 degrees, or pi over 2. And then 30, 60, 90, so 60 is actually pi over 3 here. And you can actually label this triangle the same way that we labeled our triangles from last year. So across from 30 degrees is 1. Across from 60 degrees is root 3. And the hypotenuse of this triangle is 2.
Wait, how did you get pi over 6?
So the reference angle is the angle that you see in here. Okay, or if you are uncertain of what that reference angle is, if this line right here is pi, and this is 5 pi over 6. If I do pi minus 5 pi over 6, it's like 6 pi over 6 minus 5 pi over 6, which gives me pi over 6 in between that space. Okay, I'm looking for this little piece inside here as a reference angle. Yeah, Fayak?
So the reference angle is always just like, let's say any number, like 5 over 6, let's say just remove the top number and that's it.
Well, we don't really use reference angles unless we're working with special angles. So our 3 special angles are pi over 6, pi over 3, and pi over 4.
It's always like that.
Yeah, so you'll either see pi over 6, pi over 4, or pi over 3. So this one you see pi over 6, so that's going to be your reference angle. Okay? Good? Okay, so we're also going to use the cast rule like we used last year. So we placed our angle in the correct quadrant. We formed an angle with the reference angle and made our triangle. And then we're going to kind of do these two at the same time. We'll calculate the ratio and also use the cast rule to decide on the sign of our ratio here. So I am taking the sine of an angle, which is in the sine quadrant. Does that mean my answer will be positive or negative?
Positive. Positive.
Yes. So this will give me the positive sine of the reference angle, which is pi over 6. Okay, using the cast rule. And then sine of pi over 6. So I'm looking to use SOHCAHTOA here. Sine is opposite over hypotenuse. So if this is my reference angle, this one is opposite, and this one is hypotenuse. So it will be 1 over 2, positive 1/2. Okay, if you guys switch your calculator over to radian mode, you can check your answer by actually entering in the sine of pi over 6, and you should get 0.5 on your calculator. Okay, so I'm going to expect all of these. If you're working with a special angle like pi over 6, pi over 4, or pi over 3, we're leaving these in exact values. We do want to make sure throughout the next few units that our calculator is in radian mode. We're going to be working exclusively in radians. If you're not sure how to switch your mode over, I can show you at the end of today's lesson. Okay, we're going to try another one here. So I want to place 7 pi over 4 in my grid here. So if I'm working with pi over 4s, I'm splitting the top into 4 equal slices, 1, 2, 3, 4. And the bottom into 4 equal slices, so 8 slices total, 1, 2, 3, 4. And then I'm going to count around by pi over 4s until I hit 7 pi over 4. So this is 0, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, and there it is, 7 pi over 4. Okay, and I don't need the rest of these, so I'm going to erase everything except for that 7 pi over 4. Okay, you don't have to do this method. Like if you want to switch between radians and degrees and then plot it that way, that's totally fine. I just find this is maybe a bit, like once you get used to it, it's a bit of a quicker way, and then you'll always know where your radians are within the quadrant. Okay, I'm going to make a triangle. A right triangle with the closest x-axis here. We never use the vertical lines. We're always using pi or 2 pi. So this is 2 pi here. Can somebody tell me what my reference angle is? What's this little corner inside here? Pi over 4. Yeah, so there it is there. Pi over 4. So I'm working with the 45, 45, 90 triangle from last year. So the pi over 4, pi over 4, pi over 2 triangle in radians. Okay, the side measurements here are 1, 1, and root 2 for the hypotenuse. Okay, and then we'll also just write out the cast rule here. So cosecant is a reciprocal ratio. What is cosecant the reciprocal of?
Sine.
Yes, so cosecant is the reciprocal of sine. Cosecant will be positive where sine is positive and negative where sine is negative. So I'm taking the cosecant of something in the cosine quadrant. So my answer will be negative, right? It will be the negative cosecant of the reference angle, which is pi over 4. Okay, so because cosecant is the reciprocal of sine, if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. So I'm looking for, based on this angle, this interior angle here, this is hypotenuse, and this one is opposite. So this one is negative hypotenuse, which is root 2, over opposite. This simplifies to negative root 2. Okay, so this is the exact process that I would expect to see from you. I want to see that you place the angle in the quadrant. I want to see the special triangle that you're using. I also want to see that you're using the cast rule so that you show me that it's either the positive or negative trig ratio of the reference angle, and then show me your ratio here. Okay? I know that your calculator knows how to calculate them. I want to know that you know the process of why these things are equal, why your calculator is spitting out these things, right? Okay, questions on these so far? Do you guys kind of remember these from last year?
Yeah.
Yeah. Okay, want to try a couple more here. 11 pi over 6. 11 pi over 6 is just before 12 pi over 6. 12 pi over 6, if I reduce 12 pi over 6, that's 2 pi, right? So if I think about 2 pi, that's like the 360 line. 11 pi over 6 will be pi over 6 before 12 pi over 6. So 11 pi over 6 is going to end up like right here. Okay, you can separate the top into 6 equal slices and the bottom, and you can count around if you want, but I think we can kind of start to get to know where these radian measurements are. So here's 11 pi over 6 radians right here. Okay, in degrees, it's 330 degrees. So if you wanted to switch back to degrees and then plot it, it's going to be right before 360, 30 degrees before 360. Okay, we're going to make that right angle triangle with the closest x-axis line. Our reference angle is this guy here. It's pi over 6. That's what this interior rotation is right here. And then I'm going to label the triangle from there. So pi over 6, pi over 3. That makes this root 3. Sorry, not root 2. Root 3, 1, and 2. Okay, always the rule is when we're labeling triangles, the smallest side goes across from the smallest angle. Pi over 6 is the smallest, okay, and it should be across from the smallest side. So pi over 6 is like 30 degrees. 30 degrees should be across from 1. Pi over 3 is the middle angle. It should be across from the middle side length here. And then 2 is the largest side length. It should be across from the largest angle, which is pi over 2.
So where'd you get pi over 3?
So this is a special triangle. This is like the 30, 60, 90 triangle from last year. So with this, we did this on Friday. I showed you guys the special triangles in the video. So with this, think of this as like your 30 degrees and your 60 degrees and your 90 degrees. That's where we got those special ratios from last year. Okay, so we're not really changing anything about the triangle other than that the angles are now measured in radians instead of degrees. Sorry? So if we're working with tan, we're working with Hayek?
So basically, if ever like over 6, then it's going to be the triangle where it's like 1, 2, and then root 3.
Yep.
And then if it's ever over 4, then it's 1, 1, 2.
Yep, or you might have a pi over 3 in your ratio as well, and then you're using this triangle also.
The one that's 1, 1, and root 2, right? Or this one?
This one, if you have a pi over 3.
Okay.
Yeah. Okay, so sorry, what would we be working with tan? Opposite over adjacent, right. So I'm taking the tan of something in the cosine quadrant. What does that mean? Negative. So the negative tan of pi over 6, using this as our reference angle, this is opposite and adjacent. Okay, so tan, TOA, SOHCAHTOA, is opposite over adjacent. So it will be negative 1 over root 3. Rationalized, if we rationalize the denominator, that basically just means get rid of roots from the denominator, and we multiply the bottom and the top by the root. So what ends up happening if we were to rationalize, and I just show you this because this is what your calculator is going to show you, if I rationalize this, I get negative root 3. And then root 3 times root 3 is root 9, which ends up being 3. Or root 3 squared, the root and the squared cancel, and we get 3. So either of these answers are acceptable. I'm fine if you leave it here. But if you want to rationalize, that's fine. But your calculator will spit out this answer if you check on your calculator, if you have like one of the ones that leaves it in like root format or radical format. This is the better, more mathematically correct answer, negative root 3 over 3. Yep. Pardon? So the 11 is basically telling us where our angle is, what quadrant it's in. Well, it has everything to do with it, because if my angle was just pi over 6, it would be positive 1 over root 3, right? So the 11 tells me what the angle is and what quadrant it's in. And then from the cast rule, we can determine whether that's positive or negative. Just like if I'm working with 30 degrees versus 330 degrees. The reference angle is still 30 degrees either way, but 330 degrees is in the cosine quadrant, so it makes the ratio negative.
Why don't we put it to the 10? Why is it negative 10
Well, negative tan 11 pi over 6, tan of 11 pi over 6 is negative in and of itself. So if I had a negative in front of that, those two negatives would cancel out and it would make it positive. Okay, so you guys remember the purpose of the cast rule is telling us like which ratios are positive in which quadrant and which ones are negative. In the cosine quadrant, the reason why cosine is positive here is because cosine is adjacent over hypotenuse, and this is the positive x-axis, and hypotenuse or radius of a circle is always positive. Whereas opposite, when I go down, this is technically negative 1 here. So if I do negative 1 over root 3, that's why we get the answer for negative 1 over root 3, because I'm going down on the x-axis or the y-axis here if I go down to that point. Okay, secant of 3 pi over 4. So we're going to place our angle. If I'm working with pi over 4s, I'm separating into 4 equal slices on top. So 1, 2, 3, 4. And if you need to continue on the bottom, if you don't get to 3 pi over 4, you can continue. But we start with 0, 1 pi over 4, 2 pi over 4. And there's 3 pi over 4 right there, so I don't need to go any further. Okay, so we don't need these anymore. This is pi. We're going to make our right angle with the closest horizontal line or x-axis line. What's the reference angle? Pardon?
Is that great?
Yep.
So we're going to be all the 2's there too. So it's 1, 2.
Yeah. What's the reference angle here?
Positive 4.
Yes, it's pi over 4. That's the measurement inside here. So I'm using the pi over 4, pi over 4, pi over 2 angle. Or triangle, I should say. What are the side measurements for this one?
2, 1.
No, 1, 1, root 2 for this one, for pi over 4. So this is an isosceles triangle, right? So I should have 2 equal sides if I have 2 equal angles, pi over 4 and pi over 4. The opposite sides should be equal. Okay, let's talk about the cast rule as well. Secant, what is secant the reciprocal of?
Cosine.
Cosine. So secant will be positive where cosine is positive and negative where cosine is negative. So if I'm taking the secant of something in the sine quadrant, it will be negative. Okay, so I'm going to get the negative secant of our reference angle, which is pi over 4. And because secant is the reciprocal of cosine, I'm looking for adjacent and hypotenuse, but instead of adjacent over hypotenuse like we do for cosine, yeah, we'll do hypotenuse over adjacent. So this is the adjacent side. Remember, this interior angle is my reference angle here. So this is adjacent and hypotenuse. So I'm going to do hypotenuse over adjacent for this one. And this just simplifies to negative root 2. Okay, questions for that one? Are we all kind of getting it?
Yeah.
Okay. Same process as last year, just using radians. Okay, I want you guys to try this one out. We're going to find the value of all 6 trig ratios for 5 pi over 3. So I want to plot that angle where it is, and then I want you guys to find the sine of 5 pi over 3, the cosine of 5 pi over 3, tangent, and then the 3 reciprocal ratios. Okay, so same process as before. You're going to plot your angle, make your special triangle, and then you're just working with opposite, adjacent, and hypotenuse and the cast rule to decide on what these ratios are equal to. Okay, so I'm going to give you guys a couple minutes to try this out, see what you can do with it. Okay, if I'm working with 5 pi over 3, yeah, think of it as 10 pi over 6. So you're splitting your top quadrant into 6 equal slices and your bottom into 6 equal slices, and count up until you get to 10 pi over 6. Okay, so I've taken a second here and I've just written out, I've divided everything into 6 equal slices here, the top and the bottom, and I've counted up all the way to 10 pi over 6, which we can see reduces to 5 pi over 3. So I'm just going to erase these out because we don't need the rest of these. And we're going to create a right angle triangle with the closest x-axis. So don't use the vertical line here. So it's going to be with this closest x-axis here. And your reference angle, you're not going to be using 10 pi over 6. Use the reduced angle here. We're going to use pi over 3. That's the interior angle here. So that tells me that I should be using the pi over 6, pi over 3, pi over 2 triangle that we learned on Friday. The 30, 60, 90 triangle from last year. So this is pi over 3, pi over 6, and the right angle. Across from pi over 6 should always be 1. Across from pi over 3 is your root 3. Yep. And then across from your right angle or your hypotenuse should be 2 here. Okay, you should also make sure you're using the cast rule here. We are in the cosine quadrant. And because pi over 3 is the reference angle here, that's how we label the sides. We label them according to where pi over 3 is. So this is opposite, hypotenuse, and adjacent. And then we'll just go from here. We're going to use the cast rule and we'll use SOHCAHTOA. So sine in the cosine quadrant should be negative, and it's opposite over hypotenuse. So we should get negative root 3 over 2 for this one. Okay, now that I have sine, I should be able to get cosecant relatively easily because it's just the reciprocal. So I'll do negative 2 over root 3. Or if you want to rationalize your denominator, you'll get negative 2 root 3 over 3. But either of those are fine. Okay, cosine is positive in the cosine quadrant. So it's going to be positive, the ratio will be positive, and then we'll do adjacent over hypotenuse. So it will be 1 over 2, positive 1 over 2. Okay, secant, because it's the reciprocal of cosine, will just be 2 over 1, which will reduce to 2. Okay, and then tangent is also negative in the cosine quadrant, so we'll have a negative ratio, and then I'm going to use opposite over adjacent for tangent. So we'll get negative, square root 3 over 1, which reduces to negative root 3. And then for cotangent, I'm just going to use the reciprocal, so we'll flip around and we'll get negative 1 over root 3 for this one. Okay, so there's our 6 answers there. Sine, cosecant, cosine, secant, and cotangent, and tangent. Any questions on this one? Okay, so we're going to make sure that we get to know the special triangles and how to label the sides, which sides go across from which angles. There's only 2. And then, yeah, you just kind of make sure you know how to kind of count around that radian circle that we learned on Friday. Jeremy?
You don't have to use sine curves and tan when calculating this. You just take the negative root 3 over 2.
Sorry, like if you're calculating in your calculator?
Yeah, like get the final answer, just do root 3 over 2 or something. The first one, you don't do sine.
So if you want to calculate in your calculator to check, you just type in this exact thing into your calculator. And if it gives you a decimal, you just check that that decimal is equal to negative root 3 divided by 2. So this is what you're entering into your calculator if you want to check.
Okay, so is just the negative root 3 over 2 the final answer?
The final answer, yeah. That's what the ratio is equal to. Okay. Last one for today, application. Nicole is flying a kite at the end of a 50-meter string. The sun is directly overhead, and the string makes an angle of pi over 6 with the ground. The wind speed increases, and the kite flies higher until the string makes an angle of pi over 3 with the ground. Determine an exact expression for the horizontal distance between the 2 positions of the kite along the ground. Why the sun is directly overhead is important, I do not know. Okay, so imagine we're flying a kite here. Nicole is somewhere over here. And here's the ground. Oops. There's our ground. And if you imagine there's a kite kind of flying in the air, she's holding it, and that kite string is 50 meters. Okay, so we'll say from there to the kite, that's going to be a 50-meter kite string. And it tells us that this string makes an angle of pi over 6 with the ground. Pi over 6, I want you guys to think 30 degrees, so I kind of tried to approximate this at 30 degrees here. And then I'm just going to kind of connect this because we're going to be working with triangles here, so this is just like the kite's actual height above the ground here, so making a right angle triangle. Okay, here's our kite up here. Okay, the wind picks up. So imagine that we're flying this kite, it's up in the air, and the wind picks up. What's going to happen to the kite if the wind increases? Jeremy? Yeah, it's going to go up higher into the air. So our kite is now somewhere up here. Okay, the kite moves up, it gets blown by the wind. Okay, so maybe we'll call this kite position number 1. And now it moves up here. This is kite position number 2. Okay, now we have an angle with the ground of pi over 3. Okay, and that's the entire angle here. So I'm kind of just marking that off as the full angle. And this kite is some height above the ground here. So I'm going to make another triangle kind of within this triangle, a right angle triangle. Has the length of the string changed? No, it's just moved. So this is also 50 meters. The kite string is still the same. Okay, here's the question. I want to know the difference between the horizontal position of where this string is versus or that position, not the string, but where the kite's position is. So I'm really interested in how this horizontal position has changed. If I could find the length of this little green section right here, I'm finding essentially the horizontal distance between those 2 positions of the kite, right? This is really what I'm interested in. How far apart did they move horizontally? Okay, so I'm going to call that, let's say, x. That's kind of what we're looking for, the distance between those 2 things. Does anyone have any ideas as to how we might be able to calculate this? Fayek?
Well, I solved for the first triangle, like the smaller one,
Yep.
and it's 25 meters on the side,
So which side did you solve for?
the horizontal side.
The bottom? Yeah. Okay.
Like, well, I solved all of it, but like it was like 25 meters on the vertical side, sorry,
Okay.
as well. The horizontal was 28 point, like rounded.
Okay, so this one's asking us for exact values, so we want to use our special triangles, special ratios for this. So if I know that whole distance, and if I could potentially find this distance right here, what would be the relationship between x, y, and z?
Minus y minus z equals x.
Great, so x is going to be equal to y minus z if I can find it. The larger length subtracted by the smaller length will give me this remaining length here. Okay, so if we separate this out a little bit here, I should really be able to use similar triangles to be able to figure this out. Okay, so let's just look at the very first triangle here, because it can get a little bit confusing when all of this is all together. This is pi over 6, 50 meters, and this is our y. I'm interested in what is y. Okay, well, let's look at its similar triangle. This similar triangle here, this comes from the pi over 6, pi over 3 triangle. Okay, if this is pi over 6 and this is 90, I know this must be pi over 3, right? Well, let's look at the side measurements of this. It's 1, root 3, and 2. So we're just going to use scale ratios here to figure this out. What did I multiply my base triangle by to get 50 meters? What's the scale factor here? What's the multiple?
It's divided by 2 for vertical side.
So it's 25, right? I'm scaling the triangle up by a factor of 25. So this entire y length here, what happens when I scale root 3 up by 25? What value do we get? I think we're not going to actually find a decimal here. So no decimals, exact value. So it should be 25 root 3. And that's in meters. Okay? Alternatively, if you wanted to calculate this using adjacent and hypotenuse, you could say the cosine of pi over 3 is, the cosine of pi over 6 is equal to y over 50, and then just sub in the value of cosine of pi over 6. I think using the triangles is a little bit easier. You'll have to use the triangle either way, but you can use SOHCAHTOA and set up like cos of pi over 6 equals y over 50, and then sub in the exact value of cos of pi over 6. Okay, so we've got y. Y is equal to 25 root 3. Now I want to look at the dark blue triangle here. And that is pi over 3, pi over 6, and we know this is 50 meters again.
Why are we timing it by 25, sorry?
So to get from 2 to 50, I had to have multiplied. I must have multiplied by 25. So I'm just figuring out what that scaled factor is.
What did they divide by?
Okay, so I'm going to use scale ratios again. Again, what are we doing to get from 2 to 50 here? What's the scale factor? Still 25, yep. So this one just so happens to be the same. So times 25. I'm now interested, this is my z side right here. I'm interested in finding that, and the way I'm going to find that is from 1. So if I scale 1 up by a factor of 25, what is z equal to? 1 times 25, 25 meters, great. Okay, again, I'll show you the alternative here. If you wanted to find z, you could have used pi over 3, or you could even use pi over 6 as your reference angle, and you could have set up the cos of pi over 3 equals adjacent z over hypotenuse 50. And then you could have plugged in the cosine of pi over 3. So if I look at my triangle here, the cosine of pi over 3 is 1 over 2. And then I would just be isolating for z from there. So you would end up getting 25 either way. Liam? We're almost done here. Can you wait like 2 seconds? Okay. Okay, so you can do it that method, or you can just set up the two triangles and use the scale, find the scale ratio.
Isn't it, for the other triangle, isn't it root 2 is the hypotenuse?
Yep, but there's no pi over 4 in these triangles, so I'm not using that triangle. It's only pi over 3 and pi over 6.
Oh, okay, so we're using the same triangle twice, basically.
Yep. Okay, so if x equals y minus z, x must be equal to 25 root 3 minus 25. Okay, and then oftentimes to simplify this expression, because I have 25 and 25 in each term here, we would common factor out the 25, and it would be 25 times root 3 minus 1 meters. So this is the exact expression for the length of x. Okay, so I'm just common factoring. Factored form is technically simplest form. Questions on this one? Can I clarify anything? Simran, question? You're good? Anyone? No? Okay. Great.